In order for us to understand what is the least upper bound, we're going to have to first to understand what is the maximum. So let us go through the first definition you're having here. Let A, this is the first definition we're having here, let A be a non-empty set of real numbers. I think this is clear for everybody what this sentence means. So what is the maximum? M is the maximum of A if M is in A and X is less than or equal M for all X in A. So the meaning of a maximum value in a set, it has to have two conditions. The first one is that it have to be in A, and the second condition is that it has to be greater than or equal to all the values in the same set. That is the basic and simple definition of what is the maximum. Maximum is a value that is within the set itself, but at the same time, it is greater than or equal to all the values in the same set. So if you take any value in the set A, it will be either less than that maximum or equal to it. We're going to go through the example, but it's going to be at the end of the lesson because I'm going to try to sum up for you all the idea. That is the first thing. And the same thing goes for the minimum. The minimum is a value which is in the same set, which is A, and it is less than or equal to all the values in A. That is the basic definition of the maximum and minimum. So now, going from here, we're going to try to understand what is an upper bound and a lower bound. So let's go through the second definition here. Let A be a set of real numbers. A number M is an upper bound for A. X less than or equal M for all X in A. Now, this definition is very similar to the maximum, except for one difference. If you can notice that difference is that the upper bound does not necessarily has to be in the set, which is different than the maximum. The maximum is a value that has to be in the same set, but that's not the case in the upper bound. If I've been dealing with a set and if I've been asked to give an upper bound for a specific set, my upper bound doesn't have to be in the same set. I can bring any value that is just greater than or equal all the values of the set. So an upper bound is a value that is just greater than or equal to all the values in the set. And we will see that in the examples after all, which is the same thing that goes for the lower bound. The lower bound is a value that is less than or equal to all the values in the same set. And it doesn't have to be in the set the same as for the upper bound. So what we have understood about the upper bound is that it works as the same as the maximum, except that it doesn't have to be in the set. We will see that very clear in the example I'm giving, but it's going to be just after finishing all the definitions, because I want to make this very simple and short for you. So I think now we have understood what is an upper bound. An upper bound is a value that bounds a set, and that value just if I say an upper bound, it is a value that bound above the set, and it doesn't have to be in the set itself. For the lower bound, it's a value that bounds the set from below, and it doesn't have to be in the set. And I hope this is clear to all of you guys. Now, let's go for the last definition, which will explain for us the lesson, which is the least upper bound axiom. Now we have understood what is an upper bound and what is a lower bound. going to be very clear to us now to understand the least upper bound and the greatest lower bound. So let's suppose that we have a non-empty set of real numbers. A. Alpha in R, real numbers, is a least upper bound. Now this is where we get into understanding the lesson. Now we know what is an upper bound. Least upper bound means that I'm going to read the definition and then I'm going to explain it. So alpha in R is a least upper bound for A. If alpha is an upper bound, now we all know what is an upper bound, which is a value that bounds the set from above and is greater than or equal to all the values in the set. And alpha is less than or equal m for any upper bound m of A, which means that alpha is the least upper bound. So it means that when I talk about upper bound, we have multiple values of an upper bound. We don't have a single value. You can bring up to infinite values of an upper bound. So you can bound a set with infinite values. But when I say the least upper bound, it's that I'm choosing the least value that is bounding the set from above. I hope this definition is clear. The least upper bound is an upper bound itself that bounds the set from above, and it is the least one of those upper bounds. And it works the same as the maximum. And we use this because in a lot of examples, sometimes there's no maximum for a specific set, but there is a least upper bound for that set. It means that I can bound the set without even having to have a value within the set. That is the benefit of this definition that can give us a bound without it has to be in the set. So the same thing goes for the greatest lower bound. And the greatest lower bound is we know that the lower bound is an infinite values that bounds the set from below. We have infinite values that you can bring that is less than or equal to the values of the set. And having the greatest lower bound means that I'm having the greatest value of all those lower bounds, which for me, I'm bounding the set from below with that value. So in the least upper bound, we have a unique value. And the same thing goes for the greatest lower bound. For the upper bound, we have infinite values. Also for the lower bound. I do hope, guys, that the idea is clear for you. And let's just go through the example. It's a very simple example, and there are a lot of examples. There are easy examples, there are hard examples, but the idea is this. A maximum is a value within the set, and it is greater than or equal to all the values of the set. An upper bound is just a value that is greater than or equal to all the values of the set. The least upper bound is the lowest upper bound we have for the lowest upper bound we're choosing from the values we have specified as a upper bounds. So let's go through the example quickly. Suppose that I have a set A, and I have values in the set. Let's say that I have 1, 2, 3. Now, is it clear for us that the maximum of A is a 3? Why? 1, it belongs to the set. 2, it is greater than or equal to all the values of A. And the same thing goes for the minimum. 1 belongs to A, and it is less than or equal to all the values of A. And that's for the minimum and the maximum. For the upper bound, an upper bound is just a value that is greater than or equal to all the values of A. So 3 is a value that is greater than or equal to all the values of A. 4 is a value that is greater than or equal to all the values of A. 4.5 and 10 and so on. So an upper bound is not a unique value, it is a infinite number of values that I have. And the same thing goes for the lower bound. 1 is less than or equal to all the values of A. 0 is less than or equal to all the values of A. 0.5 minus 10 and so on. Now we're going to understand what is the least upper bound, the greatest lower bound. From this example is that the least upper bound is the lowest value of all the upper bounds that I have, which is 3 in this case. And the greatest lower bound is the greatest lower bound that I have from those values. I do hope, guys, that I tried to make this very simple and short for you. I tried to just focus on the definition itself and not just go through things that we don't need to go through. And I hope this is clear for us. There are just a lot of examples we can understand and try to, um, if we have the idea as this being clarified, we can just practice on the examples and try to see more applications of the least upper bound and the greatest lower bound. Thank you for watching, and I hope this is beneficial to you, and see you in the next one.